Let me show you one of the craziest things you have ever seen in the C programming language. I'm going to write a tiny function called foo, and all this function is about to do is to assign its argument a into a local variable called b, and then print out b and then return a constant number hexadecimal 22334455. Then I'm going to write a small driving program with just the function main. All it does is to assign hexadecimal 11223344 to a and then calling foo with a. Now let's go ahead and run this program, and we're expecting foo to simply print the number passed to it by main 11223344. What the is this? This isn't the number that was supposed to be printed. If you think this is bad, watch what I'm doing now. Here I've added the local variable fooret, and I'm assigning it with the return value from foo. And now I'm going to print it. Again, the expectation is that foo will return 22334455 to main, and then main will print that. Alright, this seems correct. But what happens if I go into foo and I'm changing the first return digit to 8? Alright, so this is very weird, but we're about to see exactly what is going on here. We're also about to see that this is not just a nice trick, but a hideous bug that sometimes happen even in production code. We'll also see how to prevent it from happening, so keep watching. So what is going on with that program? In order to understand more, we first need to look into stack operations in C programs. If you don't know what a stack is, don't worry. All you have to know is that it's an area in memory used by functions for their operations, including communicating inputs and outputs between them. The rest you'll get in this video. We see here the program's memory with the program's instruction in it, and the instruction pointer or the program counter that is going over the instruction and executing each one. On the right, somewhere else in memory, we have the stack that is governed by the stack pointer. In this diagram, addresses grow from top to bottom, while the stack grows in the opposite direction. Things can be pushed onto the stack and also popped later, which will cause the opposite effect. On some systems, there is also a base or frame pointer, which allows for generation of simpler code by the compiler, since the stack pointer can potentially move all the time, while the frame pointer will stay fixed for the duration of the function. And this is the stack frame with everything that is needed for the function to operate: the arguments, the return value, and the space for local variables. Now let's combine together program execution with stack operations. Putting it all together, when main is about to call foo, it will first push an argument onto the stack. The instruction pointer will then move to the next instruction, which is the call instruction. When the call instruction is executed, the return address will be automatically pushed onto the stack. The return address is the place where we will be coming back to after the function has been executed. The instruction pointer have now arrived at an area of the function called the prologue, which is code created by the compiler in order to prepare for the function execution. It will first push the base pointer onto the stack, assign the base pointer with the current stack location, and then move the stack pointer such that there is enough room defined in order for the function to execute. After the function's code, there is code inserted by the compiler called the function's epilogue that will prepare the return value for the calling function and then return to the calling function. Eventually, the stack pointer and frame pointer will be restored and main will continue execution. Now that we have seen this nice theory about how things work, let's see it in real action. I'm going to use the debugger to see what happens to the argument A when it moves along until it gets into foo and becomes foo's B. If you don't get every detail, don't worry about it. At the end, I'm going to show you a summary for the good case and for the bad case of how A was doing its way into B. That's the most important part to understand. So first, let's zoom to the interesting part, and you can see our stack pointer expressed in the ESP register and the frame or base pointer expressed in the EBP register, which means that this is the memory space assigned to main on the stack to operate on. This is also the lower part of its stack frame. And we are starting from the instruction that will set hexadecimal 11223344 into the memory location that is A. And here it is on the stack. Now keep a sharp eye on registers EAX and EDX. This is because the CPU represents 64-bit numbers, with two 32-bit chunks glued together, both in registers and in memory. So now the code generated by the compiler moved the value from the memory location of A into EAX, and then a 0 into EDX, together making our value in 64 bits. Now the code will move the stack pointer by 8 bytes to make room for future use. It will push EDX and EAX onto the stack for the called function foo to consume as the argument. Now take a good look at the address after the call, because this is where we will land when we will be back from foo. And as we discussed, this value is going to be placed on the stack when we call foo. We make the call and there it is on the stack. And now we are in foo's prologue. The base pointer is being pushed on the stack to be saved and then immediately assigned with the value of the stack pointer in order to start a new work area for that function. EBX is saved in order to be used. And now the stack pointer is being dropped by a full hexadecimal 24 in order to make enough room on the stack for this function to operate. And now this is the stack frame for foo. Notice that the stack pointer keeps moving upwards to lower addresses, at least for now. I've skipped a few lines, and now the prologue is going to take our argument prepared for us by main and put it to a temporary location on the stack in order to use it later. And there it is on the stack. And now comes the crux of the matter. In order to assign the argument in the blue rectangle and move it into the memory location that is B, I've put a green rectangle around the memory location of B. And there it is. If we go ahead and look in the debugger will also think that B has the right value. So later when we make the call to printf, we're going to see the correct value being printed out. This is how things look like when everything works perfectly. Now let's quickly go and see how they'll look like when they don't. Again, let's zoom in into the interesting part, and we can see A was assigned, and then we quickly move into pushing it to the stack as an argument for foo to consume. But this time the code did not arrange for the right hand D word to be zeroed. Soon we'll get to moving this into the temporary location. What will be moved there? Oh my, half of the correct number was scooped up. But then on the right hand, we have something completely unrelated. Now this value will be moved into B. And what do you know? The final outcome is very different than what we have expected. Also, the debugger thinks so. And this is also the value being printed out. Alright, so even if you didn't get every detail, that's fine. Let's compare the way that A was doing into B in both cases. And as you can see on the good case, the argument was properly prepared as a 64-bit value, while on the bad case, for some reason that we will show shortly, the calling function did not put in place everything that is needed for a 64-bit value. The call function then consumed the value as if it is a 64-bit value, practically taking some garbage on the way. So now you realize what's happening here. There is a mismatch between what the calling function is doing to what is being done in the called function. The calling function is preparing arguments on the stack, but the called function thinks that there are other things than they are, and it's taking garbage. You might be asking now, how is that even possible? How this entire thing was created like this in the first place? This is made possible because of how the compilation and linking processes work. The compiler goes file by file, compiling high-level language into machine language. But when going over a certain file, it does not know what's going on another file unless we tell it explicitly. The linker then comes in, linking all those products into one working program. But the linker is merely doing some substitution of symbols into actual addresses. It will not help us if there is a mismatch between what's going on in one file to what's going on another file. So what is the thing that we need to explicitly say to our compiler? In order to explain that, it's time to reveal the difference between the good and the bad programs. I'm going to scroll a little bit up on the good working version of the code, and that is it. This single line of code is a difference and is omitted from the bad version of the code. In this one line, we tell the compiler how the prototype of foo looks like. Now some of you might be furious at me right now. He tricked us. We know all about headers. You have abused the headers. What do you expect? Well, not so fast. Such header abuse definitely happens in production code, Probably because the compiler allows us to do that. And believe me, when this happens, the bugs look like crazy magic. Also, I'm about to show you momentarily a bad way to fix that problem, also something that happens in production code. So this matter might be more dramatic than it seems in first look. Before seeing how to do it correctly, let's spend just a little bit of time seeing the other direction where we were able to corrupt the return value. So here I've placed us at the end of foo, which is the function's epilogue, and we are right on the instruction where the function is going to prepare the return value for the calling function to consume. It's doing so by moving our number into the register EAX, which is the agreed place for the return value to reside in, and then it performs the rest of the work required to exit the function and go back to the calling function. And now we have landed in main right after the call to foo. Some stack space is being released by adding to ESP. Remember that the stack grows in the direction of lower addresses and then shrinks back when released by moving ESP to higher addresses. Now the instruction CLTD is about to be performed. What this instruction does is to enlarge a 32-bit number to become a 64-bit number. This is done by something called sign extension. If the number is positive, it will be padded with zeros from the left, but if it's negative, it's going to be padded with ones to the left. In this video's description, I have added a link to another video of mine describing 2's complement, and there you can have a full explanation about what sign extension is. The bad surprise here is that sign extension is supposed to be applied only to signed numbers, meaning numbers that can be either 0, positive, or negative, but foo is trying to return an unsigned number. But we have already seen the reason to that. Since this is a version of the code where we don't have function prototype declaration, when the compiler is compiling main.c, it does not know what foo is supposed to return. Therefore, it will default to an int. And going back to our code, let's execute CLTD. And you can see that EDX is now filled with hexadecimal FFs, which is all ones in binary. We continue to execute, and eventually the number is being printed out, and the number now is that sign extended number with all those leading FFs. So as you can see, this is another manifestation of the lack of sync in the knowledge of what is going on in each of the files. And at this point, let me just add that I've used prints in this video to demonstrate the problem and solution, but there are also other types of bugs that can be caused by that kind of corruption. For example, comparison logic that can give wrong answers and so on. Okay, now that we see why it's so acute to do prototypes correctly, let's see how to do them correctly. So in order to see how to do headers correctly, we go back to the version of the code without the prototype definition. And first I have a small confession to make, and that is that I've never showed you how this program builds. Let's do that now. As you can see, when we build this program, the compiler does give us a warning, even though we haven't enabled all the warning. And it effectively says, look, I don't know what's going on here. I'm not familiar with that function that you are calling, but I'm going to proceed. How does it proceed? By using defaults. It just assumes things on the function that we are calling. Now let's start with the quote-unquote fix of declaring the prototype ad hoc and see what happened. We rebuild the program. Now we don't get that warning because we have explicitly told the compiler how the call function looks like. And from now on, we will also add the -W all parameter to our build line in order to get all warnings. The best practice is to always build with all warnings enabled, since this way the compiler can help us catch many bugs like the ones we are seeing in this video. But now let's go and see what happens if we go to foo and change its definition. Something that can definitely happen in real-life production code. Things are changing all the time. We rebuild, and what do you know? We don't get any warning. This situation is worse than we had before, where at least we got some information from the compiler. Now we're explicitly misleading the compiler by giving it information that is no longer true. So we think of a header file as something that exports definitions from our module to external modules that are consuming our module services. However, I would suggest to think about it as something resembling a Java interface. It stands by its own, and it's not only exporting definitions, it's also dictating definitions inwards into the module. So to implement that, we're going to create a new header file. The header file is internal to what we define here as the module that contains those two files, and it will just reside here in the same directory. We are going to call this header interface.h, and it will include the original prototype definition for foo. Now we're going to remove the ad hoc prototype definition from main, and instead we're going to include our interface header. And importantly, we're going to include the same interface header in foo.c. Now both files are being fed by the definition in interface.h. Now we're going to build, and as you can see, it fails because the definition in interface.h conflicts with the actual function definition in foo.c, which is exactly what we want to happen when we accidentally create a discrepancy in the code. Now we go and we revert that definition in foo.c, rebuild, and now everything is perfect and locked together to prevent future problems. If you find this analysis powerful, please go ahead, like and share, so you will be notified when more deep understanding low-level material comes out. See you.